All right, so welcome back to System Software. We are in the middle of our section on the file system. Last time we looked at, kind of from a high level, the design of file systems, hierarchical file systems, which are still in use today, a similar kind of design. And today we're going to see how to actually program against this file system. The kernel calls, the operating system calls that we can use. You've used some of these for your classes, but we're going to dig into a little bit about how the system is designed and how to actually use these system calls properly. But before I move on, first, are there any questions about last time, questions about logistics in the class, issues with the project? So we've got the VC exercise, which is going to be, it's due today, due tonight actually, and then the Hello project due next week, it looks like. Questions about these exercise or projects? No, everybody's good on these? Yeah.
When might the feedback be available for VC exercise?
For VC, well, it'll be after the due date. So all of them we won't run after the date. I will ask the TA Sanan to run this, tomorrow. So that exercise should be pretty fast to grade as long as my scripts aren't like broken. It should be pretty fast, but I'll let him know. I'll make him aware that it's due tonight. And remember, it's due at 11:59 p.m. And we can see via the Git timestamp when you actually turn stuff in, and we'll clone it, soon after the due date, so that you can't do any manipulation of the log. Other questions about the VC exercise, about Hello? All right, let's go over the homework from last time. So I think this is the homework. Questions on this homework? Shall we go over it?
Yes.
Okay, let's go over it. So let's mark this. This is homework 5. Let me make this easier to see. So this is just a little exercise to help you see the difference between absolute and relative paths. So let's construct this tree. And we'll start with just the first one, home. So is this an absolute or a relative path? Absolute path. And besides, me telling you it's absolute, how do you know it's absolute? Got the forward slash, and the forward slash represents what directory? Forward slash at the beginning. That's the root. In the Unix-like file systems, the top level directory is always root, even if you have multiple devices. They just get attached to the file tree under a directory name. Okay, so where does home live here on this directory tree? Yeah, what? Off of the root, right? This is a child of the root directory. This is where home is. Any questions on that? Any disagreement? Any other thoughts? All right, what about /dev? Also, sibling of home. Okay, and here's the first kind of trick question. We have the /boot directory, but our working directory is /dev. So how does the working directory used to figure out where on the file tree you are? Or when is it used? What's that? Yeah, for relative paths. This is an absolute path. So does the working directory have any information that you need in order to figure out where? No, it doesn't have any information. So where does /boot go on this file tree? Yeah, sibling, child of root, sibling of home and dev. Okay, any questions about these first three so far? Absolute paths? Okay, let's get into the relative paths. So it's relative because it doesn't have a forward slash. Where on this file tree is the USR directory, the USR file? It's also a file. It's on the root. How do you know it's on the root? It's a relative path. The working directory, yeah, good. So if you have a relative path, if you want to know the absolute path, if you don't know where on your file tree that file exists, then you just take the working directory and append it to the relative directory. So in this case, we get the working directory with, the directory name or the path, the relative path, plus the working directory, and we get /usr. So this is yet another child of root. Questions on that? Yeah. Because boot is an absolute path. So absolute paths, you don't need to know the working directory. It tells you, starting from root, where to find this file. It tells you every subdirectory from root to find this file. So that's what I was saying, this is like the first trick question. The working directory doesn't have any influence on absolute paths. If you have the absolute path, you don't need to, the only reason you need to know the working directory is if you have a relative path, is because you don't know whether this is, we'll see the other examples of this, you don't know which parent Paul is in, the Paul directory or the user directory. You don't know what its parent directory is without knowing the working directory. Okay, so that's USR. What about Paul? Is this a relative or absolute path? It's relative. And where does it live on this tree? Is it a child of root? No, it's a child of home. So again, we take the working directory and the relative directory, and we join them. So to make a full path out of it, you join it with the / delimiter. And this tells us the full path to finding this file in the file system. So we start at root. The first directory to look at is home. So we start at the root, look at the home directory. And then the next file inside that home directory is called Paul. So this is a child of the home directory. Questions on that example? All right, so let's do, our first kind of more complicated relative path. Let's do ... home / Paul / source. All right, so this is a little bit of a more complicated one. So to do this systematically, take your working directory and join it with your relative path. Join it with the path delimiter, and we can just do this procedurally. Start with the root directory, so we start here, the root directory. And then what's the next directory that we enter in order to continue this path? Go to dev, right? So we go from here. Let me use a different color for this. So we start here. Didn't actually change color. Start here. We go to dev. And then the next path is what? The ... directory. So strictly speaking, the ... directory is a child of dev, or at least it's in dev's directory map. But it's linked, hard linked to the parent, which is root. So if we go to the parent directory, that's an alias to, or we go to the ... directory, that's an alias to the parent directory. So we are, in a sense, back in root. Questions on that? Does that make any sense? Or does that make sense to everyone? Questions on that? Okay, so now we are back into the root directory. So this kind of first part of the path here could be replaced with just root, right? Okay, and so what's the next path we enter? Home. And then the next path is Paul. And then finally, a file called src. Questions on that one? Okay. All right, let's keep going. So now we have a path called bin, a relative path bin, and it's under the user. /user was our working directory, the path to our working directory. So where on this file tree does this bin live? Child of user. And now we have our next kind of trick question here. We have a couple of tricks in here. One, it's called ./bin. So let's do this systematically, just like we did with the one that used dot. So we take home/Paul, and we take ./bin. And again, let's go procedurally through this. So first of all, notice that this file, bin, has the exact same name as this bin. But is it the same file? It's not the same file, and here's how we'll know that it's not the same file. So let me get rid of this path, and I will instead do this path. So we start at root, we go to home, then we go to Paul, and just like with dot, we have a dot directory here, which is aliased to the directory itself. So when we follow the dot path, we follow the dot path here, and it's alias to Paul, so it puts us right back in the Paul folder. And then we have /bin. So I didn't do this in an ideal way. Let me make this, give myself a little more space. Oops. Go to the dot folder, and then that brings us back to Paul. And finally, the last file in this path is called bin. And because we're now in the Paul folder, it must be Paul bin. So even though it's the same file name, bin, it's under a different directory. So we don't violate this, uniqueness constraint that every file must have the different name in a directory. Questions on this? Is that hopefully clear to everyone? So this is why you can refer to multiple files, and depending on what your working directory is, or refer to the same file, depending on your working directory, you might be actually referring to a different blob of data on disk. All right, let's finish this up and do the last two. All right, so here we have the home folder again. So we already have one file here called home. Let's look at this home file and see if it's the same one. So again, we take home/Paul as our working directory and join with home. So it looks kind of confusing because home appears twice in the path, but are these the same file? No, they're not the same file. So under which directory is this home directory? It's under Paul. So we have another child under Paul. And now one more confusing one. Our working directory path has a dot path in it, but where on the tree does this Paul folder live? Under home of the one that's under Paul. Let me go through it. So we have a complicated working directory path here. /Paul. So this /dev. Start at root, we go to dev, we go to the parent folder, that's aliased to root, go to the home folder, Paul, and then we go to this home file. This file that is a child of Paul, which is a child of home, which is a child of root. And under here, there's yet a different file called Paul that is under this home directory. Questions on this? Yeah.
What's the significance of this working directory ending in a slash when the other one's done?
I just was being sloppy and being sloppy. So probably should not have ended with a slash. If you allow slash in the names of files, it's very confusing. So it's either prohibited or it has to be like escaped. I can't remember what they do in Unix, but yeah, you can ignore that. There was no significance. That was just me being a little sloppy about this. So strictly speaking, you shouldn't put this slash here because it's not actually part of the name of home. It's a file separator without anything after it. But in the kind of on the command line in the Unix world, you can autocomplete will put the slash for you so that you can continue writing the path, and it'll ignore the slash if you use it on a directory for change directory. All right, other questions about the homework? Hopefully everybody's good on file system, at least. So hopefully, at least from a user perspective, you can see a little bit what's going on under the hood. And one of my goals was to have you never wonder where are my files, or at least be able to navigate the file system. So hopefully this exercise will help. All right, any other questions on basics of file systems, homework, projects? Okay, so today we're going to talk about system calls. This is your main interface to your operating system, to the kernel of your operating system. You can think of your kernel as just a big library that is between you and the actual hardware. So you can think of the purpose of system software, and what we cover in this course is this bridge between the kernel and applications. I had this picture in the beginning. Down here we have all the different kinds of hardware, computing hardware. There's the CPU, memory. There's lots and lots of variations of these. ARM chips are becoming really popular because of mobile devices and some laptops. And there's huge variance and differences even between the same type of device, like RAM, CPU. Then we have all sorts of peripherals, keyboards, monitors, both for consumer devices and even like large-scale computing devices, which may have different types of peripherals, different types of shared memory, different types of network connections. And so for an application developer, if you're trying to write, say, a web browser, it might be very annoying if you have to handle both wireless cards and Ethernet cards, different types of storage media, if you have to maintain code for every type of processor you have out there. So the kernel and the system software provide intermediaries between your applications and your hardware. And the kernel provides two important things. It provides an abstraction of the hardware, so that instead of having to write programs that have to be aware of hard drives versus solid state drives versus IDE versus SATA and all the different types of hardware buses, instead you can just say, I want to write files. So files are that abstraction of hardware. Files are one of the main abstractions of hardware. It also provides sharing of resources. So if you've ever wondered why it is that you have one chip on your device, one RAM stick, yet you can have thousands of browser windows open, it's because of this ability to share resources. So if you try to run a program and a program's already running, your kernel will just happily run both programs, even though only one at a time can actually use the processor. Did you guys learn about this in like architecture? Didn't learn about this? It's called multitasking or multitasking or multiprocess or time slicing. But yeah, the basic concept is you have maybe one SSD drive, one processor, but you can run multiple programs that are reading and writing to disk apparently at the same time and that are running at the same time. They look like they're running at the same time. But what's actually happening is the kernel is very quickly sharing resources, very quickly swapping between the different programs that are running on the same processor. So this actually, how this is done is really for like an operating systems class. But we're going to look at how to use the kernel to actually create processes, create files, work with I/O. And one of the side benefits of this kernel design is that not only does it abstract away hardware into a simpler, consistent interface that you can use across different actual physical devices, it also protects the hardware from users. So if you have multiple people working on a server, you may not want every user to be able to just read and write and directly control your hard drive, because if you have files on there, they can blow them away. There's no protections. If you have a programming bug, even if you're a single user on your device, you may have a bug that blows away memory that may destroy other processes. So your C program might blow away your web browser's memory, and then that will crash, or your entire kernel can crash. So one side benefit of this is protection of the hardware from programs. And there's this concept in the operating system world of the separation, the boundary between kernel space and user space. So So just to diagram this very briefly. So when you do something like call write, to write to a file, if this is my, I'm going to use the hard drive symbol here. That's a very ugly hard drive symbol. So if I've got a hard drive, and I know your consumer devices don't really have them anymore, but I think data centers do. So this is your physical disk. When you call write, you're writing some data to your disk. You think you're writing it to the disk, but you're not directly interacting with that hardware bus or making any changes to that hardware. Instead, you're just making a library call to the kernel, and then inside the kernel are implementations of read and write operations that work on this disk. So if you instead have, say, like a USB jump drive, so if you have a USB drive, if your file resides on that USB drive, you don't need to write different code to write to it, even though under the hood, the hardware bus is completely different. There may be different timing, there may be different codes that you have to send to these devices in order to make data reads and writes. You just use the write function. And so this is where this kernel space is abstracting away these differences in hardware. Yeah?
I have a question about USB drives.
Yeah. Okay.
So there are certain devices that won't be able to read a USB drive if it has too many gigabytes. Like it has to have a minimum amount of gigabytes, and then it can read it. Otherwise, it just won't.
A minimum amount of gigabytes?
Yeah. So like.
I didn't know. Okay.
I
didn't know that.
About, like,
I mean,
I can't read certain USB drives because they're too big.
Oh, you mean the USB drive is too big?
Yeah. So the USB. So I'll give you the example of my problem. So
Okay.
cars, they can only read 16 gigabyte USB drives or lower. Anything higher, and it won't register.
Yeah, it's either the physical USB device or the kernel. The implementation of the kernel doesn't have support for that type of device. So I don't know the exact situation. I'm not a hardware person either, but there are standards for these drives, and it also just might be they only have a FAT file system, which is a type of file system that is limited in how large you can have any disk at all in that file system. So I'm guessing it's in whatever their kernel implementation is, they don't have drivers. So drivers are these chunks of code that you can add to the kernel space so that write will now work with that device. But you as the user or use the application developer, you don't need to care about that. That's a kernel problem. So you may need to install new drivers or update your kernel. I mean, it's a car, so it probably gets updated every 10 years or something. You need to install some other drivers so that it'll work with whatever different kind of hardware or whatever different kind of file system is on that drive. But yeah, that is actually closely related to this interface. So whatever application you're trying to use on the car, oops. Whatever application you're trying to use on the car is just expecting that the kernel will support that device. But if there's no code in there to abstract that hardware away to provide an interface, a read-write interface, then yeah, your hardware is not going to work. Okay, questions about that? So if you take an operating system class, you'll learn about the internals of this kernel, how this kernel is actually implemented. And in these drivers, this is part of what makes the file system exist. So the file system doesn't exist per se on disk. All the disk hardware can do is read and write sequences of bytes. It's the kernel that provides this illusion of a file system by managing directories and file names for you. Yeah?
So the kernel is basically just checking that you can do that operation without breaking the system?
It's more than that. So in the case of files, it's managing data structures on disk that are used to represent files. So like we talked about last time, the blob of data, the blob of bytes for, say, an MP3 file doesn't have the name of that file. The name of that file is managed by the kernel. So the kernel maintains additional structures like those directory files and other structures store the blobs of data on disk in a kind of efficient way. And the interface it gives you is the file system interface. You can give paths, you can read and write individual files, but the disk itself just reads and writes bytes at addresses, numeric addresses. So this disk hardware has no concept of a path or a file name. It's this kernel that provides that illusion to you, the developer, as a way to manage data on disk. I don't know if that kind of answers it. That's very high level, but if you look at how, take an operating system class, and they'll talk about how file systems are actually designed to provide that illusion to you, to provide that hierarchical file system to you. All right, other questions on this, just this concept, the separation between this kernel library and user space? So what this means is when you're programming in C and when you're reading and writing files, you're not actually even really directly touching hardware at all. This is all being mediated for you by the kernel. Okay, so within this class, the reason I'm telling you this is because what we're going to be programming in this class is the system software. And the system software is code that lives, well, as I showed in this diagram before, is the code that lives in between the kernel and applications. So even though, yes, the kernel provides this hardware abstraction, there's lots of other useful stuff that application developers don't want to necessarily have to write. For instance, programming language compilers. So if you're writing an application, you don't necessarily want to have to write in assembly. You may not want to do all of the low-level read-write operations yourself. If you've ever used printf, printf is not directly calling the kernel. It's yet another library that itself is calling the kernel. We'll talk about this in a little bit. And so in order to write and understand system software, we have to at least understand the kernel, at least how it's used. And so today in this class, I'm going to show you the kind of Unix style of using the kernel, using system calls, so that we can then do projects where we actually implement some system software tools. Okay, so the main way we actually interact with the kernel and indirectly interact with our actual machine, with our actual physical hardware, is through system calls. And system calls in C, if you use system calls in C, they look like nothing more than just functions. They're function calls in C. But they're special function calls because they're not backed by code directly. Instead, they switch into kernel space. So when you make this write call, the system will switch into the code already written for the kernel. And the kernel exposes this system call interface to do all sorts of management of your hardware. So managing processes, creating and destroying new programs that are running, managing memory, reading and writing files, doing networking. And hopefully everyone's reading this Linux programming interface book, but in this book, there's a nice diagram that shows this, diagrammatically shows this difference between user mode and kernel mode, or user space and kernel space. And it even shows some of the assembly code that's used to switch between the two. Yeah?
So when we use malloc and calloc in C, so we're actually calling to the kernel to make that memory?
So actually for malloc and C, those are also like printf, those are also user space libraries. Under the hood, they're calling a function called sbrk, sbreak, which asks the kernel for more memory. But effectively, yes, when you're calling malloc, you're indirectly asking the kernel, I need more memory space for my variables and my data structures. And with printf, that library is saying, hey, I need to read and write this data to some physical disk or some physical hardware, and then the kernel will do that for you. But yeah, good question. I'll show you at least how to see the differences whether something is a kernel call or a system call or a library call. But okay, so you can think of system calls as just a kind of a more elaborate form of a function call. So function calls, we'll see how function calls are actually implemented in the compiler in the second half. But what's kind of an intuitive definition of a function, or what's the behavior of a function call? What does a function call do when you make a function call? When you write your own function, what happens when you call it? What's that? Well, yeah, all the code does that, right? All the code tells you something in the program. But what is it when you say, say you write a function called square, and then you call that function. You say square parentheses. What happens when you call square parentheses? Yeah.
It jumps to where that function is.
Yeah, it jumps to the code in that function, starts running that code, right? And then when it's done, it goes back to where you called it. So that's like the basic semantics of a function. And system calls conceptually, they work the same way, except instead of just calling code in your program, instead it switches to the kernel code. So the kernel code is living in memory, basically always living in memory at a special location in memory that you cannot read or write. And instead, in order to switch between kernel mode and user mode, it uses a special, at least in the x86 world, uses a special technique in hardware called an interrupt. Did you guys learn about interrupts in computer architecture? Okay, some people are saying yes. So interrupts are basically an event-based system in hardware. So if you have new data coming in on an Ethernet line, then the hardware will signal the processor and say, hey, you have data on this line. It's called an interrupt because it interrupts the process, it interrupts the execution of a program on the hardware. And the way the kernel mode switch is implemented is through what's called a software interrupt. You as the developer can write code that will cause the kernel to stop, or cause the processor to stop what it's doing and start running the interrupt handler. So anyway, operating system class will actually go into details how this works, but I'll just show you diagrammatically. Yeah.
Is it a precautionary, like mention the user is not able to edit straight?
Yeah, it is. So especially if you have multi-users, like if you're on Eustace and I could just read and write to storage or RAM anywhere in RAM, uncontrolled, then I could say, look at another student's homework, right? Or I could steal somebody else's password or steal somebody else's code. So the hardware, the protection between the kernel and user mode also provides like security for the hardware and between users. And even without malicious actors, it also provides a reliability against mistakes in your own coding. So you wouldn't want your seg fault to destroy your your Word document that you're working on and destroy your essay for English class. So anyway, the actual mechanism of how this works is really more for an operating system class. But if you read this, do the reading, and it'll go over briefly this divide. But basically, you have code that's pre-written, library code in the kernel that's resident in memory, and then when you do a system call, there's the hardware gets involved to actually switch between user space and kernel space. So the reason this switch happens is because in kernel space, that code does have free access to the hardware. It can read and write memory wherever it likes. It can access physical devices, storage devices. Whereas the user space, when you're in user mode, the hardware, no instructions will be able to write to hardware. Okay, any questions so far? I know it's really high level. It's more for an operating system class, but any questions on this? Okay, so let's get into actually using Syscalls, or Syscalls for short. So system calls, I'm going to use the word Syscalls for short. You'll see that in the book as well. Just like I mentioned, they're just like C functions. And there's a special C library that handles this switch between user mode and kernel mode. So it will take your parameters, it'll trigger the interrupt, and then it'll collect whatever return values there are. So here's my syscall. It's called execve. This will run a program for you. Inside of the implementation of it, there's a little wrapper that will switch into kernel mode for you, and it takes whatever arguments you give it, and it puts them into memory for the kernel to have access to, and then it calls this interrupt, the software interrupt, and the kernel mode will look at which system call you're making. So it's basically a giant switch statement. It'll look at where that code lives in memory, and then it'll run the actual implementation of that execve code. So it's just a lengthier way to go from this call to the code that actually implements that function, so that we can have this kernel mode protection. Okay, so let's look at some documentation of these things. So this will be useful as you're actually doing some system programming, because these the names of the functions are pretty intuitive, but how they're actually used is can be a little subtle. So firstly, if you type man syscalls, it'll show you the list of all the syscalls that are available in this system. So notice that fopen doesn't exist here. So you probably, who's used fopen? Used fopen, right? So fopen is not a syscall, it's actually a library call into the C standard library for working with files, but under the hood, there's a open call. This will open, this is what fopen calls in order to open files. But yeah, you can see, in the Unix world, the Linux world, there's lots of system calls. So, there's dozens here, probably over 100 different system calls. So that's where you can just see which system calls are available. And the man page separates out system calls versus library calls. And we can see this in the man page for the manual itself. So if we look at man's man page, manual, manual, then it'll tell you which section of the manual holds which information. Now, if you don't tell it which section to look at, it will just try to find whatever matches in your documentation. So for instance, if I look for open, you see here it found a program in section 1 called xdg open. That's not really what I was looking for. I was looking for the open syscall. So I can tell man which section I'd like to see information in. And so man 2 is the section for syscalls. So if I say man 2 open, you'll see here this is open from section 2. This is the system call that actually will call into the kernel for opening. And if I look for fopen, the C library function, doesn't find it in section 2. Section 3 has all of the C library calls that you're probably, you're used to using. So man 3 fopen, this will show us fopen from section 3, which is the library calls. And yeah, here they are. Here's the documentation of it. So when you're ever, yeah, go ahead.
So we ever use the first section of man?
Oh yeah, so the first section of man has the executable programs. So when you're typing like man ls, it will find whatever section matches, has some match to it. And so yeah, you can, if you know it's like a command, a common command, then yeah, you can say man 1, or you can just say, you can omit it, and then it'll try to find which try to find a match. Yeah.
Is it different for Mac? Because when we're doing man syscalls, it's just not working.
It might be different for Mac, yeah. So Mac is like BSD Unix, it's not Linux. I don't know why it doesn't have, they just don't have syscalls in their documentation, I guess. Man syscalls. Okay, yeah, so just here's some more examples of looking for the man pages. So I use these periodically because I can never remember the interfaces to these. These interfaces are really specific, especially for the kernel code. Yeah, and they'll show you all the other variations. Okay, so these are probably the library calls you've used frequently for C class, for learning C, fopen, fprintf or printf, fscanf. These are the library calls. Under the hood, these are calling the system calls. And these are the kind of equivalents of these. We have open, write, and read. Oops, and read. So when you're programming in C, it's made even easier for you. I know it doesn't feel like it's easy, but it's made easier for you because fopen, fread, fscan, fwrite, fscan, these are actually part of the system software. This C library is meant to make it easier to use the kernel. And to see why that is, if we look at, say, fwrite or fprintf, you can see printf takes a string, and it's a format string. You can put like %d in it, for instance. But the system call for write is a little bit more Spartan. You can't you can't give it a file that you've opened by name. You have to give it a so-called file descriptor. We'll talk about that when we actually get into actually using this program. You have to give it a buffer. It's not a character buffer anymore. It's not text-oriented. And it has a slightly less intuitive interface. It'll write up to count bytes. You tell it how many bytes you want to write. And it may not even write all those bytes. The kernel may be interrupted, something may go wrong, and so you actually, as the user, have to manage making sure actually everything that you wanted to write out gets written. You have to manage this buffer really carefully. You have to make sure you don't have buffer overreads or buffer overwrites. So the interface is a lot more Spartan. It's a lot more simplistic, which is why everybody teaches the C library calls instead.
Does it only show for like the C language, or can you make it show other languages as well?
Well, C is like the system's programming language for Unix. So when it comes to the system calls, these are all for you, at least for the system calls. These are all for C. These are all intended for C. There are like foreign function interfaces for other languages, like I think Python probably have some wrappers for calling them, but yeah, C and Unix were like designed together. And Unix was written in C originally, or at least now, yeah.
If you like download Linux, does it also automatically come with it as well, or not?
Does it automatically what?
Like if you have Linux,
Yeah.
does all this? Because this is all we don't have to install anything. It's just automatically on the computer.
It's on use. Yeah, that's the Linux distribution. So those maintainers will package the kernel. Linux is just the kernel code. It'll package it with all the system software. So all this stuff that I'm using, like Bash, LS, man pages, these are the system software. These are the system stuff that is being packaged with the kernel and shipped out to you and organized for you ahead of time through like vast installation scripts. Okay, so that's kind of a really high-level overview of system calls. The main point is that you have this kernel mode that has raw access to your hardware and protects that hardware and the management of these data structures like file systems and memory management, protects them from user space applications. And so but exposes system calls, exposes these entries into the kernel, which allows users to manage this hardware in a safe way. So when you write applications, you're writing them in user mode, and the only way you can get access to the hardware is by using a system call, which the hardware switches into kernel mode and then runs some predefined, pre-written code that will then interact with the hardware on your behalf. Bless you. Okay, and then we saw the difference between C library calls and system calls. Okay, the reason we have library calls is because dealing with the kernel is, as I said, it's a much simpler interface. So dealing with it is a little bit more nuanced. The Unix way of doing syscalls is basically very DIY. So whenever you call any syscall, the kernel will basically, if it can't do something, or if something gets interrupted, or if something goes wrong, everything is on you, the programmer, to handle those errors. And as we'll see in the man pages, there are many, 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 many more error things that can go wrong than things that can go right. So you, as the system software implementer, needs to be able to be aware and how to manage this error state. And this is actually good practice for any programming or any system development, to account for all the possible ways things can go wrong in your application rather than being optimistic in your code. Okay, so here's some code of how a syscall, a kind of standard system call with error checking, looks. So hopefully this part at least should look pretty familiar, right? This just looks like a C function call. So we have this open syscall, Open takes a path. Well, hopefully all know what a path is now. And it takes some flags to say whether we want to, in this case, it's read only, it might be write only, it might be read write. And we get this file descriptor. So this file descriptor is close to that inode number. This is close to what the file really is under the hood. So it's not that file object you get from the C library. And then you can see 4 times the amount of code is written for doing error handling. So in this case, if we look at the man page for open, it says the return value of open is a file descriptor, small non-negative integer that's an index to the entry in the process table of file descriptors. But where are errors? So lots of description. These are all the flags you can pass. And then here, down in errors and return value. So every one of these pages for the system call has a description of the return value. So it says on success, it returns the new file descriptor. That's just effectively a pointer to your open file. On error, -1 is returned, and error number is set to indicate the error. So this is like the standard interface for Syscalls. You have some successful return value, and then you have some special value that will set an error code. And there's this global variable called error NO, error number, which you can inspect to figure out what the error was. As you can see here, the number of possible errors, the number of things that can go wrong in opening a file is many. There are many things that can go wrong. And as a careful programmer, you wouldn't want to assume that things are always going to go right, because then the rest of your code is going to just break, going to assume things are right. And you can go to really fine level of error handling in programming systems using C and Unix. You don't have to do extensive error handling in this class, so I'll give you all of the errors you need to handle and what you need to do. But I just want to get you in this mindset of make a syscall, check for errors, handle that error. And this is really any kind of system building. If you're building an airplane, building a mechanical device, just optimistically assuming everything's going to go right leads to pretty brittle devices. So basically every system call will have some error state that you'll need to check. And this is what it looks like. So the man page will tell you what the return values are. So in this case, -1 means there was an error. And so we can check that by just checking the return value. So we save the return value. If it goes well, we've got an open file. If it doesn't go well, then it'll be -1. We can check that. The error handling for this class is going to be super simple, so all we do here is we just print out an error message and then exit the program. Questions on this? Questions on this? Simple example. Has anyone written code like this? Like nobody? So when you take C, they don't teach you to check for errors? They do a little bit? Okay, so some people have. Okay, so I went over the documentation, return value and errors. Let's look at some of the errors could be. So E-access, requested access to the file not allowed, so you don't have, sorry.
I was going back to the previous about that. So if it fails, like let's say with the open, we're trying to access like an illegal piece of memory or illegal file.
Yeah.
Why wouldn't the system just crash there before we reach the error?
That's a good question. Why does the system just give up whenever there's an error? Or, you could, right? You could design a system like that. But imagine you're in your web browser and you go to you type in a domain name that doesn't exist, and then your browser just shuts off, it shuts down. Or your whole machine shuts down, right? Your whole machine is like, all right, I got an error state, let's just give up and restart. So what it allows for is it allows for error handling. It allows for having fault resilience in your system. So, this is really a good practice in any programming, is you think of errors not as outside your program, where if anything goes wrong, well, we're done. You think of errors as just a special kind of data in your program, a special kind of input or output. So when you're thinking about an algorithm or a design, you think about all the possible inputs to your program, and you think about all the possible outputs of your program, including error states, like what happens when something goes wrong, and you build that into the design of your algorithm or your system. So I was being a little flippant with the machine shutting down, but that's why. That's why. It's because the kernel doesn't dictate how you handle errors. It just tells you, hey, there's an error here. You can do something about it. So in this case, you might give it a message that says, hey, you don't have access to that. Try again. You can put this in a loop and say, hey, give me another file to open, right? Or you could just crash and say, as the user, you can be like, or as the developer, I can say, well, I don't want to handle this user who gave me a wrong program. I'm just going to quit. So it gives you that flexibility to design the system how you like. Yeah, I got a question. So try-catches are like a programming language construct for doing error handling. Yeah, exactly right. So yeah, we don't have try-catch in C. This is like Java and C++, but yeah, exactly right. Try-catch is actually like a programming language construct that for baked into the language of design for doing error handling. So Java kind of famously introduced try-catch blocks so that it has a very sophisticated, actually C++ did this as well, I think. Is that right? Try-catch blocks for building error handling into the design of your software. C is much more rudimentary, so we just have really basic function calls. We don't have try-catch blocks. We don't have special objects for exceptions. So it's all done very manually. It's kind of like manual stick driving your car versus automatic. And it's same thing with why would you not want the kernel to do this for you? It's just like driving a manual transmission. Maybe you want to rev really fast. Maybe you want to try to save gas. Automatic transmission makes that decision for you. But here you make that decision as the developer, as the system designer and the developer. All right, that's a lot of words for five lines of code, but any other questions on this? So this code looks, I think, pretty straightforward, but it's really the philosophy about error handling that may take a little bit to wrap your head around in Unix, but I think is a good exercise for any kind of engineering. If you go out professionally, if you're writing code, most places are doing code review, they're doing automated testing. So just pushing code that you think works and without any accompanying tests or without any code review, probably get rejected, and you don't want to be the person who breaks the build or breaks the code. So there's probably, you'll see a lot more code is being spent on error handling than there is on actually writing the syscalls and actually writing the program. All right, any other questions on this? So let's see, I think I have, okay, so yeah, one more, I want to show an example of actually using these syscalls, but one little helper here. So in my first version of the code, I kind of manually wrote out this fprintf. Anyone know what fprintf is? Have you used fprintf? Okay, a little bit, yeah. So prints to a file. So the file here is standard error. We're going to talk about this when we talk about I/O and processes. But there's a helper function you can use called perr. This is not a syscall, this is a library call. And it'll automatically interpret this error number for you. So this error number is gonna be literally a number, it's gonna be an integer. And these are macros that map to that integer. The perr function will look at those numbers and it'll give you a more meaningful error message, basically. It's kind of an automatic, it's kind of like an automatic error message generator for you. Okay, so here's a full example of a program. Let me switch to the actual code. Let me do this. All right, here's my complete error number example just to go through it. There's a lot of header files for these, for the system call stuff. So unit is like Unix standard. This is like the standard set of syscall definitions. This is for the error handling stuff. This is flags for open. And yeah, you're probably familiar with these, standard I/O and standard lib for library calls. All right, so what does this program do? It reads in one argument Then it sets that argument to the path variable. And here's our program with error handling code. We call open on that path. If it succeeds, then according to our man page, it'll be 0 or more. If it fails, then it'll be -1. And this error handling code will be triggered. This is also an example of the close syscall. Works the same way. You give it the file descriptor, and it'll either try to close the file. If it can't, you'll get a -1. All right, questions on this full code, this complete code? Hopefully pretty straightforward. I think you've seen argument handling a bit. All right, let me build and run this. Okay. So let's take a file that exists like errorno.c. Oops, forgot to do /. So nothing happened here. Didn't do anything. So why is that? I ran the errorno program. I gave it errorno.c. I see no output. Why is that? Yeah.
Prints to a file.
No, it doesn't print to a file. What does this program print? Yeah, go ahead. Yeah, it's just opening and closing the file. These print statements only happen when there's an error. And there was no error to opening this path. It exists, so there's no error. But if I try to give a path to something that doesn't exist, so what happens? This argument is stored in argv1. argv1, that file name is passed to open. And as we can see with the errors, I think it's probably access. Oh yeah, probably access. I think it's access. Actually, I don't know if it's access. Probably no exist or something. I don't actually remember. I don't remember which one it is, which error it is. But it triggers one of these errors, and because the syscall is designed to return -1 when there's an error, this code path is executed, and I get my P error being printed out, just to kind of convince you that so this is what gets printed out when the program fails. This is successfully opened. This is what happens when you successfully open a file. So there's my print statement. That's what happened when it fails. It means I entered this code block. But if I give a file that it can open, never enters this code block, and instead continues executing the program. Questions on this? All right, let me get into. I'll just gonna kind of quickly overview some of the file system management syscalls that we have. So we've got the stat call, and you can see we actually saw this last time when I ran the stat command. Stat will give you metadata about the file. It'll give you all of the timestamps, like when it was last accessed, modified, changed. Give you number of hard links, size information, which device it's on, permissions information. And this is, the documentation of this structure is documented in the stat library. So this is all, you're gonna get this data structure back when you call the stat command on a file. And there's further documentation. I'll show this more in detail. I think you'll need this for the project. I'll show this more in detail. But you can actually see flag information that's going to be contained in the structure. This is very much the kind of low-level C way of managing data structures. The data structures are super simple. They're all structs. There are lots of integer constants being used in them. I'll kind of walk you through carefully how to use these. These are the documentations of open, read, and close. And we'll also look at data, where's the file? And we'll also look at directory management. But yeah, I think we don't have time to get into this right now because we only have a few minutes left in class. So let's save this for next time. We'll actually get into the nitty-gritty of using system calls for file systems. We have another lecture on system calls. So let's go over this next time. And yeah, have a good weekend, everybody.